The other probability distribution that falls under continuous distributions is exponential. So a common example is time between arrivals. This is a big one for business. You want to know how much time there is between customer arrivals. And this is the equation that Excel does for us. Just want to note that 1 over lambda is both the mean and standard deviation for exponential distributions. That'll come into play a little bit later on. Just note that lambda is still the same as the lambda that we saw in Poisson. Okay, so Poisson lambda was the average number of discrete things per unit of time. So average number of customers per day, and 1 over lambda, we're using that same lambda. Okay, so just a note about Poisson versus exponential. Remember for Poisson, something like number of arrivals per unit of time. Lambda was the mean arrivals per unit of time. Lambda is the same thing for the exponential distribution. It's just that the mean and standard deviation is 1 over that. So for discrete, we have x being 0, 1, or 2, whereas continuous, we're talking about a range or an interval. So something like waiting time until the next arrival. So number of customers in line versus the time in between customers. Okay, so just a quick note about lambda. If you're given average time in the problem, then you have 1 over lambda, and Excel needs lambda. So if that's the case, you may need to find lambda. If you're given average unit per time, then you already have lambda for the Poisson and exponential functions. So you don't need to do any converting. So just be careful. Look for whether you have 1 over lambda in the problem, average time, or lambda in the problem, average discrete thing per unit of time or space or distance. Since lambda is useful for calculating both exponential and Poisson probabilities. Okay, let's look at an example. Let's say X is the time it takes to service a customer at a bank, and suppose the average service time is 5 minutes. What is lambda? Notice lambda is not 5 minutes, because lambda is always an average discrete thing per unit of time, space, or distance. So that 5 minutes, the average service time, is actually 1 over lambda. And I have to convert that, or I have to solve for lambda in order to do the Excel function. So 1 over lambda equals 5 minutes. So if I solve for lambda, lambda ends up being 1/5 or 0.2. Okay, so just be careful of that. If you're given average time, then that's 1 over lambda, and you need to find lambda. But if you're given average discrete thing per unit of time, then you already have lambda. So lambda is 0.2, and I want to know the probability that the time it takes is less than 4 minutes. Notice that I could say less than 4 minutes here or less than or equal to. It doesn't really matter because exactly equal to 4 is just 0. Okay, so we will use the expondist, abbreviation for exponential distribution, and I want to know less than 4 minutes if the average or lambda is 0.2, and I'm going to do true. For all less than or greater than problems, it's true, and I'm never going to have exactly equal to in chapter 7 because of continuous variables. Okay, so about 55.07 probability of taking less than 4 minutes. Okay, what about the probability that wait time will be greater than 3 minutes? Okay, so now I want 1 minus because it's a greater than problem, just like we saw in chapter 5 with the discrete distributions. If I have a greater than problem, then I need the complement rule. Okay, so 3 minutes, and I want 1 minus, so equals 1 minus exponential distribution. 3 minutes, lambda is still 0.2, and I say true. So the probability is again about 55%, 54.88%. So if I was rounding, it'd be 55%, so A. Okay, so let's try to distinguish between some of these distributions. Number of defective units in a batch of 30 units. That's going to be binomial because you have a maximum number of 30 units, so that's your number of trials. And each thing has 2 possibilities, defective or not. Remember, that was a characteristic of binomial. 2 events, and there's a number of trials. How long we'll wait until the next customer arrives? If you're talking about time, then we're talking about exponential. Whereas the that last one there, the probability of 10 customers coming to the ATM on a given day, you're concerned with probability of customers. So since you want the probability of a discrete thing, then that is Poisson, not exponential. Okay, so some decisions around this. There's too much time to service a customer at a local oil change shop, so processes need to be streamlined. We need to make things faster. Traffic at one ATM is quite high, so we put in another ATM. And here are just a summary of the Excel commands for the normal distribution and exponential distribution.